This is Gary Kildall, and this is Armatron, our noisy little robot here. We're using Armatron to demonstrate some of the basic things that a robot can do, and even though this is a small toy, it really does demonstrate those things. For example, this robot has a shoulder, which can turn along that axis. It can lift by its shoulder or come down. It's got an elbow, which it can bend. It has a wrist, which it can move, and it has a hand, which it can open. And it can actually do something that humans can't do. It can twist its wrist around that particular joint. Now, Gary, this is a small example of a robot. It's certainly not a computer. How do computers and robotics relate?
Well, there are a whole lot of devices that fall in this category of robots, and they go from the simple show robots all the way up to a sophisticated assembly line type of robot. And in a show robot, for example, there's a human operator that somehow is communicating with this device, making it roll around, giving it brochures and things of that sort. But as we add more intelligence on board, then that's where the computer comes into play. The computer then controls all the devices, makes some onboard decisions based on its own intelligence.
Well, there's been a science fiction fascination with robots throughout this century, but the fictional robots bear little resemblance to today's real robots. The image of a robot has taken many different forms since the clockwork musicians and dolls of the 18th century. But during the mechanical age of the early 20th century, the robot became a frightening symbol of the future, threatening to transform the world into an over-mechanized, dehumanized society. In heavy industries, the worker was becoming an accessory to the machine, repeating the same task hundreds or thousands of times in precisely the same way. To those not benefiting directly from the new methods, mechanization of work and life called up bleak images of the future. Fritz Lang's Metropolis depicted the year 2000, a world divided between industrial barons and downtrodden workers, slaves to an underground machine city operating day and night. The drive for efficiency leads the city's master to consult an inventor who has devised the ultimate tool, a mechanical replacement for the imperfect human being. This remarkable film may not have been completely accurate in its predictions, but it anticipated a fictional idea of robots that persisted for decades after it, a human-made, human-like mechanism that behaves like its creator. More often than not, the machine tended to destroy its creator as well, prompting writer Isaac Asimov in 1947 to devise the first 3 laws of robotics. These prescriptions assume either a large degree of intelligence or, interpreted another way, programmed behavior, one of the principal criteria for modern robotic systems. While not usually designed with human characteristics, post-war robots were, from early on, capable of programmed motion. Servo mechanisms or feedback-controlled robots began to appear in the late 1950s. From 1960 on, robots became useful adjuncts to a number of industries, particularly in jobs that were uncomfortable or hazardous to humans, like welding and painting. Repetitive functions as performed by the machine like humans in Metropolis were being taken over by robots with more human-like capabilities, including sight, touch, and error detection. In some of the latest applications, CAD/CAM systems work directly with a robot arm to transfer the design of a part from the video screen to the finished product.
David, I guess everybody has the idea that a robot should go around and wash your dishes and clean your house and so forth, but I have a feeling there's a lot more to robotics than that. Can you give us some idea what's going on in the industry?
Well, industry has been using robotics for 15 years already. These are robots that are designed to do dirty jobs in industry. And they're doing them.
What do you mean by a dirty job?
Well, undesired jobs. Jobs that are hard, strenuous, dangerous, harmful, and lethal.
What is an example of something like a dirty job that would be a lethal job, something you've seen
Well,
going on?
lethal is not yet in operation. This would be in the future. I mean, by that I mean jobs in hot environment, nuclear power plants and the like. But examples of undesired jobs is handling workpieces in heat environment, hot environment.
What about in assembly language control, not control, but doing assembly processes? I know the Japanese have been very heavily involved in that. What's going on in just the industrial use of robots?
Well, that's the other kind of deadly job, the dehumanizingly dull jobs that are so common in a lot of our factories, and which Americans have demonstrated a strong dislike for, and it's the reason why a lot of our production is going offshore. And what's being done now, I think, in industry is that we're addressing those kinds of mundane assembly tasks and taking the dehumanizing jobs and giving them to machines to free up human beings for more creative, more challenging kinds of work.
Yeah, but you see, a very important point about assembly is that here the competition is very strong, because to do assembly is a very complex task, especially if it's done in unstructured environments, not when pieces are jigged. If it's done like people. On the other hand, assembly people on assembly line, people working on assembly line, are paid very little. There are a lot of women that work on assembly line, and they are underpaid. So it's a double slam. On one hand, it's complex. On the other hand, you have to compete with very cheap labor. And the labor becomes even cheaper when it goes to Mexico or it goes to East Asia. So that's where the challenge is. On the other hand, with the undesired jobs like heat treatment or die casting or forging or arc welding, where the cost for the workers is high and it's a very undesired job and it's very easy to do, that's more cost effective.
I guess one of the differentiating factors in robots that are used, say, industrial in applications of that sort, that you can build a very precise robot that, say, would weld within a few millimeters of where it should weld, or you could use, say, vision processing to figure out where the object is and to manipulate it with very coarse mechanical devices.
Yeah, or as David points out, putting the robot into a structured environment, such as an integrated work cell, where the work is presented to the robot in such a way that it doesn't require the extreme accuracy or sensory capability that some of the anthropomorphic machines currently require. Henry Ford revolutionized American industry by bringing the work to the worker on the assembly line. And we see a very similar trend as a necessary part of the evolution of robotics in American industry, where we structure the workplace to suit the robot and make the robot easier to integrate into the overall scheme. And that's really applied robotics. It's a different set of problems than the technologies necessary to anthropomorphize machines, which is the basic research being done in robotics now.
And I would like to make a very important point, I think it's an important point, and that is that people worry, about unemployment and so on. I want to make an observation, which I think is important. The number of blue-collar workers that have been displaced or replaced so far by industrial robots is very, very small. And the projection, if we extrapolate from the past for the next 5 to 10 years, is also going to have a very small impact on the labor force. Okay. And my point is that I think the main reason for this is the fact that today's robots are not intelligent. They cannot compete effectively with human workers.
Now, is that changing, though, with the applications, say, artificial intelligence and, say, knowledge-based systems? Are those a factor in what's going on?
Well, I think, as David points out, there's a whole spectrum of applications, from the very simple, which are being handled by the very simple pick-and-place mechanical devices that, for example, the Japanese would call robots and we don't, to the very esoteric applications which require lots of intelligence, lots of sensory capability. But there's a broad spectrum of applications somewhere in the middle where if you select the application properly, then in fact the machine can be very cost effective and very competitive with a minimal amount of intelligence. Ultimately, we will have to go to intelligent machines and distributed intelligence architectures where the robotic elements in a totally automated factory would be in communication through several levels of computer hierarchy.
Matt, you mentioned the Japanese, and the perception is that the Japanese are ahead of us in robotics, and you kind of pointed out a fine line in terms of defining what a robot is. What is your version of what's going on in terms of research in Japan and this country in robots?
I would say that the Japanese are ahead of us in terms of automating their factories. And their way of automating the factories is a very systematic approach of looking at a factory as a unit of production and going in and solving the problem systematically from the bottom end up, looking for the easiest applications that they can resolve, learning in the process, and then moving on to the next most difficult applications. And we see that as a very logical way of introducing automation into our factories. On the other hand, Americans are way ahead, I think, in terms of some of the technologies associated with the anthropomorphic machine. Certainly vision systems, I think we have a lead over the Japanese and perhaps some of the other sensory areas. But it's becoming a world business, and Fanuc Limited, which is one of the leading manufacturers in Japan, has just signed a joint licensing agreement with General Motors. GMF is now going to be, if not already, the leading supplier of automation systems.
Gentlemen, I have to interrupt because we're going to take a short break and then come back and meet two personal robots, Hero from Heathkit and Teach Mover from Microbot. Distributes the Hero 1 robot here in Northern California. And George, maybe you could get Hero to give us a basic demonstration of what it does.
Surely.
Hello, I am Hero, the educational robot. I have a brain, just like you do. But my brain is a computer. My owner programs my computer for me, and I always do as I'm programmed. I can talk like this, I can turn my head. I can move my arm.
George, how much weight can that arm hold?
It can hold about 8 ounces extended and about a pound when it's fully retracted.
And what kind of functional use could this arm perform?
Oh, that arm could do things like pick up items from one assembly line and move them over to another.
I can use my grip. I can move my wrist.
Does Hero have the same normal axes of movement that an industrial robot might have?
Yes, Hero has 6 axes of motion like a Class 3 industrial robot.
And I can move about. I think I made an excellent pet. I'm even without strain.
Is he finished?
Hello, I am Hero already.
It'll
Now,
stop him now.
George, before we take his clothes off and see what's inside him, tell me, I see there's a keyboard and an LED display here. What do you do with that?
Yes, this is used for data entry, Stu, and the LED display is to tell you where your information is stored within the
So you can
microprocessor.
program him through this keyboard.
Yes. Mm-hmm.
And I see you have a kind of breadboard here. What do you use that for?
Yes, that can be used by students studying interfacing circuits.
Okay, let's take his panels off and see if we can look inside Hero and see what makes him tick, if that's what he does. Okay. I'll help you with the back one if you want to get the front one there.
Easily.
Okay, let's take a look at the front here, George, and what do we have over here?
Okay, this is your main circuit board here with your microprocessor and all of the various ICs that interact with the other boards.
Okay, can I spin them around here while
Sure.
we talk?
Now, these various boards here are the sensor boards that operate with the various sensors again. This is the main drive control board. This one is the sonar transmitter and receiver board. And around here we have the sonar board and the main drive board. And around here we have the voice synthesis board and one of the other sensor boards here.
Okay, mainly you use here as a training robot, as an educational robot, right?
Yes, he's designed to be used by the student in the laboratory to study
Okay,
robotics.
well, George, thanks so much, and now we'll go back to Gary.
As Stuart joins us on the set, I'd like to introduce Dusty Rhodes and John Hill of Microbotics. Dusty, you have a device here that looks very interesting. Are you going to show us about that?
We sure will. This is our Teach Mover, which is a developmental robot used by industrial engineers to develop work cells in the factory, also for training engineers. Let me show you one of the little tricks and games it can play. This is the block stacking game. And it will find the large block and put it in the middle. The robot has a sensor that can sense how large the device is. And here it says, I have the large block, I'll put it in the middle. Now it knows to go back to the previous location for the smaller block and put it on top. I'll let it go on for just a moment and show what happens if it finds no block. Now oftentimes we go over and put the blocks in different places and try to fool it. But like a worker who's confused by instructions, if it looks for no block without work, it goes and sits down.
During the setup for this, you had blocks placed around in various positions, and it wasn't able to find them. I assume that's because the sensing mechanism isn't really doesn't have any vision and so forth. Is that going to be added to this kind of device?
That's true. John could talk about adding a vision to the work cell or to the robot.
Well, if a robot had a camera interface to it, such that the camera was looking down over the work area, the computer could process the image and locate the particular block and direct the robot to go there. I mean, that would be possible. And these instances, then the robot could just automatically grab it.
I know that David has worked with vision some. Do you have anything to add to that?
Yeah, I agree with John. You could improve this by adding not just vision, you can have range and touch sensing, not just the micro switch like this robot has, more an array of touch sensors. Also, you could add some smarts into it so it knows what it is doing, and if it makes an error, it'll blow the whistle.
David, where are we in adding smarts to robots?
Well, we are struggling. Sensors are being added to robots today, and they are applied gradually into in industry. There are other applications of robots that would have to have sensors. These are unstructured environments, such as in the military or agriculture, in medical institutions, etc., or home use too. This is an area that is very difficult because robots are too dumb today to do this job, which requires a lot of intelligence.
Do you see the field of personal robots growing as personal computers did, or robotics moving in the direction of computers?
I put my bets more on the more application-oriented robots, such as I mentioned. The hobby is okay, but that's not where the big money would be, other than on a toy level.
But if you take a parallel with I guess with the microcomputer, popularity of microcomputers and personal computers, a lot of that was a grassroots effort. The invention of the Apple, for example, by Steve Wozniak was a technical hobbyist endeavor, and it's kind of exciting to me to see robotics now come through that grassroots evolution.
Yeah, I agree with you. I think it's wonderful. I think there's a good analogy between computers and robots. Just like computers started just for commercial and scientific applications, now it's all over our life, right? And I think the same thing is going to happen with robots. And I think it's a great idea that there are a lot of hobbyists that are getting into it, because there's a new generation now that would not be afraid of robots, that would be able to apply it in many areas of our life.
David, something like this is relatively simple. I mean, it's an arm, it can pick things up and so on.
Right.
You talked before about not only replacing blue-collar work with robots, but even white-collar work. How do you do that?
Well, you saw what Dusty was doing. He was using this teaching box to tell the robot what to do. And if this information that he has in his head could be transferred into an automatic system, it could be done. Specifically, computer-aided design database includes all information that is needed to perform a certain job. Now, we can eliminate the trainer that uses the teach pendant to move the robot and tell it what to do by using self-teaching and self-calibration that all the information would be transferred to a computer, and with the sensors would tell the robot where to find things and calibrate itself and then do the job.
Okay, Gary, well, if you and I aren't replaced by robots, we'll be here again next week for another edition of the Computer Chronicles.